Okay, so welcome back. Last that we met, I gave you the following graph in example 24, and we didn't get a chance to finish it. I told you I would pick up on it on the next video, and these are the answers. So if you want to take a second, if you were one of the ones that attempted it, this is the answers that you should have gotten. Let's just make sure we understand really quickly. So when x is equal to -2, so here's when x is equal to -2, what does y equal? Well, we see this dotted line, this vertical asymptote, and that graph never crosses that vertical asymptote. So there is no y value, or in other words, the y value doesn't exist when x is -2. What about as x approaches -2? Well, let's you and I agree that if you x starts approaching -2 from the left side, notice how your graph is just going down towards -infinity. Whereas if x starts to approach to -2 from the right of it, then your graph is just going up to +infinity. So again, it's not approaching the same number from both sides, so the limit does not exist. All right, so what about f of 0? So when x is 0, what is y? So here's when x is 0. And if we just move up to the solid line, this is y. We see that y is equal to 4 when x is equal to 0. So now what about the limit as x approaches 0? So again, if you think about approaching 0 from the left of 0, this is your line, and now let's see what the graph is doing. The graph is going, it looks like it's getting closer and closer to, looks like a half. Now, what about when you approach 0 from the right of 0? Okay, well, let's see what the graph is doing. Well, it looks like the graph is, y is going to 4. So on one direction, y is going to a half, and the other direction, y is going to 4. They're not approaching the same number from both sides, so the limit does not exist. All right, f of 2, here's when x is equal to 2. Notice there's a hole in the graph, so that does not exist. And now, but look at the limit. Notice how the graph is approaching the same number from both sides as x approaches 2 from both sides, and that number is a half. So that is your limit. Finally, f of 4, when x is 4, it appears that y is equal to 2. So that is the answer to this one. But when you approach 4, as x approaches 4, it's going up to infinity from the left of 4. It's going up to infinity from the right of 4. So your graph is approaching infinity as x gets closer and closer to 4. Again, another reason why it does not exist. Okay, so let's recap. So what do we know right now? What are the methods that you know of how to find a limit? Well, one method you know is you can create a table, right? This is just a numerical approach where you the very first problems we did in the previous video, where you would just pick numbers close to the number of interest, and then you on both sides, so like say 0.01 on one side and 99 cents on the other side, and then you would try to make a prediction as what is happening at the c value of interest. Another approach is just more of a geometric approach to limits. You can just look at the graph. Okay. But in this section, in 1.3, we're now going to develop some more analytical skills on how to find limits, right? Because we don't want to be making tables or trying to draw graphs. We would like to have a much better approach, let's just say, that will still give the exact values, so without all the guesswork, but ones where we don't have to spend a lot of time on doing some preliminary work like plugging in numbers, right, on both sides and then making a guess. So what are some properties, right? Some basic properties of limits, some basic limits. So I am not going to go through each of these for you. I am going to go through the first two. And if you have a lot of math in front of you, at some point in time you want to stop just accepting things and then trying to play the game of placing it to memory, because I promise you, I don't care how good at math you were in high school. If you go far enough in this subject, I guarantee you that you're going to run out of hard drive space, right? And you're going to run out of brain power you just can't play the game of this recipe. I use this recipe when cooking this, and I use this recipe when cooking this. You're going to want to dig in a little bit more. So take this basic limit. It says the limit as x approaches c of b is b. Now, well, it says let b just simply be any real number. Okay? So now I'm going to draw this for you, and when I draw it, you're going to think, oh, well, that's like an elaborate duh. That's just a duh statement. But at that point, you don't have another theorem to place to memory, because now that you have just looked at the geometry, you'll see why this makes perfect sense. So let's pick this spot right here. Let's call that C. In fact, we'll call that C on this graph over here. So this C value is just another x value, but it's special enough that we'll give it a name C, okay? And now, what is the graph of y equals b look like, right? Y is equal to b. What does that look like? Well, since b is just a number, like for example, what does the graph of y equals 2 look like? Well, don't you agree with me that that's a horizontal line? That y always equals 2 no matter what x equals? Right? So if you were to graph y equals b, let's just say that this is the graph of y equals b. So no matter what x is, y always equals b. Then can you see why this makes perfect sense, that as x approaches c for a constant, the answer is just the constant? But because of course, as x approaches c, y is still is at b, and as x approaches c from the other side, y is still at b. No matter what, y is always equal to b. So then the limit as x approaches c of b is also equal to b. Again, sometimes mathematicians spend a lot of time up front with formalizing what would seem like very intuitive or duh statements. Okay, so what about the number 2? It says we still care about what the limit is, only now x is still, of course, still approaching c, but now the graph is x. So if you had to graph y is equal to x, what would that look like? Well, that's just a 45-degree line. This is the graph of y equals x. So now again, notice what the theorem is stating. X is approaching c. So as you approach c from the left, that would mean your graph is approaching whatever number this is. As you approach c from the right, that would mean your graph is approaching whatever number this is. And does it not make sense that for the equation y is equal to x, that means if x is 2, then y is 2. If x is 1, y is 1. Then if x is c, y is c. And if x approaches c from both sides, y is c. So these are, again, you could, if you wanted to, you could continue this game. The benefits would come later, because you're starting to really associate the geometry and the algebra. And that's how, if you want to know how if you want to know if you're getting good at this stuff, then you'll know it, because when you'll be able to think about in your mind, if I change something on the graph, how does that change my equation? Or if I change my equation, what is that doing to my graph? And you'll be able to visualize things like this. And that's how you know you're getting good at this stuff. But calling on some of these properties, here's the good news. The good news is life just got a whole lot simpler. So take, for example, and I'll come to that hint in just a second. Take, for example, the following question. We want to take the limit as x approaches 2 of the function 4x squared plus 3, right? So this equals what? That's the goal. Well, all right. So you're welcome. You could create a table. You could try to draw the graph and look at the graph of it. But here's what's beautiful about this. The properties of limits allow us simply to plug in the c value in for x. So in other words, here's another way that you can evaluate limits. You could just simply plug in the c value in the function. So in this case, we would have what? We would have 4 multiplied by 2 squared plus 3. And you could go on those previous properties. It's telling you that, yes, you can do sums and differences. You can do scalars. But all in all, what we end up getting after we plug in the 2, so we have 2 squared is 4 times 4 is 16 plus 3 is 19. Now, can you and I agree that that was much easier than doing a table and probably easier than looking at the graph? So I like this approach. Maybe you're the same way. I like the can I just plug it in approach, this analytical approach to limits. So the question I would if I were in your chair would be, well, when do I get to use that approach and when can I not use that approach? And here's my hint. So we are going to run into some scenarios where you can't just plug it in. But my hint is to always start with your substitution. All right, so always start with subbing in the value. Now, if you run into problems like you're trying to divide by 0 or 0 over 0, these types of problems, then we'll deal with those. But right now, let's start with substitution. So, for sure we can use the substitution method for polynomials. What about rational functions? Well, rational functions are just a fraction, right? But it's a polynomial divided by another polynomial. So the question is, can I just plug in this 1 in for x? And the answer is yes. Now, if you run into a problem, then I'll show you how to deal with that in just a second, but we won't know until we plug it in. Ready? So plugging in 1 squared plus 1 plus 2 divided by 1 plus 1. Okay, so fairly simple. We should get, we get 2 in the denominator. We get, what is that, 1 squared 1, that's 4 in the numerator. So we end up with an answer of 2. Much easier. All right, when else can I use this substitution method? What if it's a radical, like a square root or cube root? Can I use the substitution method? Yes. What about if it's a composite, like f of g of x type of function? Can I use the substitution method? Yes. So here's a couple examples. So you feel free to pause the video if you'd like. You're going to start off with, you want to find the limit, and we are going to use this technique where we just find the limit by taking the value of c and plugging it in for x. So 0 squared plus 4. So that's just the square root of 4, which is 2. Easy. Same thing here. So now we're dealing with the cube root. This time we're plugging 3 in for x. Well, let's figure out what that is. So that's 3 squared is 9 times 2 minus 10, so that should be 8. And the cube root of 8 is 2. Okay, so this method, this substitution method, we're going to see where else we can use it. Really quickly, just a side note. You can put your pens down if you like. Has anyone ever told you what a square root is? Well, just so you understand, we normally don't put the 2 here, because, right? But it is the index is 2. And the power of this x value in this case would be x to the power of 1. So asking what is the square root of x is simply asking you to take x to the, whatever x is, raise it to the power of 1/2. So what am I trying to tell you? I'm trying to tell you that this symbol, square root of x, is just shorthand for saying something to the power of a fraction. And that fraction would be 1/2. In fact, cube root just is another way of saying something to the power of 1/3. So that's all square roots and cube roots and fourth roots are. It's just another way of saying to the power of a fraction. It's just notation. Okay. So what about trigonometry, right? What about our trig functions? So for example, sine of x or cosine or tangent. Can I use that substitution method for trigonometric functions? And the answer is yes. So take, for example, the limit as x approaches 0 of tan of x. Now, the beautiful thing is, if you listen to me, we're going to start off with, let's just take 0, plug it in for x, right? Take their c value and plug it in. Now, you can see just from the graph that as x approaches 0, y is also approaching 0. You could also grab your calculator. Now, you want to stay in radians for this class, okay? You don't want to be in degrees. You can do calculus with degrees, but I'm telling you the formulas are a whole lot easier if you stick to radians. So anyway, if you had your calculator handy, then you could just do tan of 0, and you would see that tan of 0 is equal to 0. If you did not have your calculator handy, of course, tan of x is the same thing as sine of x divided by cosine of x. So if you knew your unit circle, and which I hope you do, sine of angle 0 is 0, and cosine of angle 0 is 1. So you have this fraction 0 over 1. And of course, 0 over 1 is equal to 0, right? Just make sure you understand 0 over 1 equals 0. 1 over 0 is undefined. Okay, it's okay to say I want 0 of the 1 slices or whatever, 0 of the 3 slices, but it makes no sense to say I want 3 of the 0 slices. That makes no sense. Okay, well, what if the trig functions get a little bit tougher? So the limit as x approaches pi of x times cosine of x. All right, well, so pi 3.14, so that would be somewhere around here, right? This is why radians are so much more beneficial, because pi is a number on your number line, just like 3 is a number on your number line. And so we can look at the geometry. You can't quite do this if you're thinking degrees, right? So 100, like this is not 180. Pi may be 180 degrees, but this is not 180 on your number line. So nevertheless, can you just plug it in? Well, yes, you can. We're plugging in pi for x. So what do we get? Well, this is going to be pi multiplied by cosine of pi. All right. Well, our only question is, what is cosine of pi? Again, I hope you know your unit circle, and cosine of pi is -1. So when x is pi, y is -pi. And you can see that from the graph. Okay, so just like in all math classes, your math professors, your math teachers, they make it easy, and then all of a sudden they take all that confidence away, right, and introduce some problems. So let's just take a look at why this is problematic. So notice that if you were to start off by substituting 1 in for x, you would have 1 to the power of 3 minus 1 over 1 minus 1. And so this, you end up with this statement 0 divided by 0. Okay, so let's make sure we understand that when you get a statement like 0 over 0, this is what we call an indeterminate form, right? And I'll write it for you. This is the indeterminate form. I don't know if I can spell it, but I can talk about it. By the way, if you see me bunch letters together, that just means I don't know how to spell it, and that's my way of hiding it, just FYI. Okay, so what you need to know is statements like 0 over 0, we call that indeterminate because it doesn't relay any information yet about the limit. In other words, we still don't know information about whether the limit exists, and if it does exist, what is it? So if you get 0 over 0, you're going to have to roll your sleeves up because you still got a little bit more work to do. All right, well then, what do you do? Okay, so in this particular case, I had the first method. I'll write that again. So method 1, if you get 0 over 0, try this. Try to factor. Okay, and see if anything cancels. So let's do that right now. So we got the limit, x is approaching 1. Let's go ahead and factor. So, well, the denominator, x minus 1, that can't be factored anymore. But the numerator, that's just the difference of 2 cubes. Right, so that would be x minus 1. The numerator factors to x minus 1 times x squared plus x plus 1. Okay, and now notice what we hope happens is that something cancels. And you can see right now that your x minus 1 factors cancel. So what's left at that point? Well, you still have not evaluated the limit, right? We still want to know what is the limit as x approaches 1. But what's left in this case is just the x squared plus x plus 1. So method 1 is to factor, cancel, and then use the sub method. So factor, cancel, and then try to use the substitution method. So now let's do exactly what we've been doing on the previous problems. Let's plug in a 1. So what do we get? Well, we get 1 squared plus 1 and plus 1. In other words, we get 3. So factoring is one method around dealing with indeterminate forms. And this method works. Obviously, it works for algebraic functions, but this is just one you want to keep in mind. This is, if you get 0 over 0, this is one way that might work. And you can see from your, I've produced the graph here, you can see what's happening as you approach 1. Okay, well, let's run into another problem. So the second method. So again, there's nothing wrong with radicals. So that's why I always suggest just start by trying to substitute. So in this case, we're going to start by trying to plug a 0 in. And then if we run into problems, we'll see what we can do about it. So if I start off, this would be 0 plus 1 minus 1 over 0. In other words, we would have what? Well, in other words, this would be the square root of 1 minus 1 over 0, which is square root of 1 is 1, so that's just 1 minus 1, or 0 over 0. Okay, so there's that indeterminate form. And that tells us to slow down a little bit. And now what could we try? Well, you could try factoring, but as you can see, there's nothing to factor. So the next method that you can try is you can try rationalizing. And particularly rationalizing the numerator. So the terminology to rationalize the numerator just means that we don't want, right now we have a square root in the numerator. We want, on any square roots, we want them to be in the denominator. That's what we're going to try to do. Okay, so I'm going to go ahead and erase this, this picture. This is just a picture of the graph. And you can kind of see what's happening as x approaches 0. And I just want to give myself enough space to do this problem. Ready? So let's take so we still got the limit as x approaches 0. Let me rewrite the original problem. So it's the square root of x plus 1 minus 1 over x. Okay. So the goal is to do the following. It's a little bit tedious, but it's actually quite ingenious if you think about it. So ready? Let's start with the goal. The goal is I want to multiply by 1. Right, literally, I want to multiply by the number 1 because I know anytime I multiply by 1, I didn't change my problem, correct? Anything multiplied by 1 is itself in this case. So, but I want to choose a way of multiplying by 1 such that I no longer have square roots in the numerator. I want all my square roots to be in the denominator. So this is right out of pre-calculus. And what we're going to choose is to multiply by the conjugate of the square root of x plus 1. So I'm going to write something and I'm going to erase it. So really quickly, the conjugate of a plus b is a minus b. Okay, the conjugate of a minus b is a plus b. And now let me show you why multiplying by the conjugate is very handy, right? So if I were to FOIL this, well, let's do it. So we would have a times a is a squared. Then you'd have a times negative b, so that would be negative ab. Then you'd have b times a, so that would be positive ab. And then finally you would have b times negative b, which is negative b squared. Now, do you agree with me that my two middle terms are going to cancel? In fact, if you multiply any of these binomials by their conjugate, that is always going to happen. So we've engineered this to happen. So in the FOIL process, if you know that the two middle terms are always going to cancel, does it make sense to you that really I could have got to my answer by just doing a times a and doing b times negative b? All right, so I'm going to erase that. And let's get back to our problem. So now, what is the conjugate of the square root of x plus 1 minus 1? Well, the conjugate is the square root of x plus 1, change our sign, so plus 1. Okay, now, if you want to multiply the numerator by the square root of x plus 1, then you have to also be willing to multiply the denominator by the square root of x plus 1. plus 1. Now, don't you agree with me that this is just a fancy way of writing the number 1? Square root of x plus 1 divided by the square root of x plus 1 is just, if you divide them, you just get 1. So really, we're just multiplying by the number 1. It's just a fancy way of multiplying by 1. Okay, so let's go ahead and continue here. So let's start with the denominators, multiplying those denominators. So x multiplied by the square root of x plus 1 plus 1. Let me give you a trick, and I'll tell you in just a second. If you listen to me, I'll save you a lot of time. Okay, so I'm multiplying the numerators, which just means I'm foiling. And let's start. So the square root of x plus 1 times the square root of x plus 1. Well, the square root of 2 times the square root of 2 is the square root of 4. And what's the square root of 4? 2. So likewise, the square root of x plus 1 times the square root of x plus 1 is the square root of x plus 1 squared, which just means it's x plus 1. Okay? All right, so now the part that I'm not going to write is the part that's going to cancel. So if I do the square root of x plus 1 times 1, that's a positive square root of x plus 1. Then if I do this negative 1 times the square root of x plus 1, I would have a positive and a negative square root of x plus 1, which would cancel. Forgive me. So those are going to cancel. I'm just going to skip to the last part of foiling, which is negative 1 times positive 1, which gives me, which gives me negative 1. Okay, so now my hint. So you'll notice that, especially if you've been doing this a while, you'll notice that the textbook problems are fairly cookie cutter. They take the same forms, version to version, author to author. So you could take this x and distribute it, right? There's no problem with doing that. What I'm suggesting is that you do not. So just leave it attached. Okay, so when you do this method, just whatever you're multiplying, just leave it attached, and you'll see why in just a second. Okay, so do you agree with me that if I drop these parentheses, that I would have a positive 1 and a negative 1 that would cancel out? So the only thing that would be left in the numerator would just be x. Okay. Now, all the way up to this step here, okay, including this step. If I plug 0 in, I get 0 over 0 on this step. If I plug 0 in for this step, I still get 0 over 0. If I plug 0 in this step, I get 0 over 0. If I plug 0 in for this step, I get 0 over 0. But notice that this x and this x are going to cancel each other. So those x's cancel, and when they do, I finally have a situation where I can plug a 0 in and not get 0 over 0. So this is what's left. And it's at this stage here that we have rationalized the numerator, and we now plug in the 0 for x. Okay, so now we use the substitution method. So that ends up with, once we evaluate the limit, so 1 over 1 plus 1, right? And that is just 1/2. That is our limit. Okay. So please be neat along the way when you're doing these problems for your tests. Notice that the limit notation does not disappear until this step right here when you plug it in. That's when my limit notation disappeared. So, forgive me, I need to get something to drink. And if this, if I continue to cough, I'll have to take a break in the video. Okay, so let me now move to two very special trig limits that you should have written down or have access to. So let me start with just stating them. So the limit as x approaches 0 of sine of x over x is 1. And the limit as x approaches 0 of 1 minus cosine of x over x is 0. Let's start with the first one. So looking at the orange graph here. Now you can see just the geometry alone, you can see how the graph is approaching 1 from both sides as x approaches 0, right? And likewise, you can see that for your second limit, that as x approaches 0, y is also approaching 0. Let me do a little bit better than that, though, besides just stating it. Notice down here, so I'm going to, if you don't mind, carry your attention down here, and after this, I will take a break, because I know you're getting tired. So kind of take notice of what I have going on here. So this orange curve is the graph of 1 over x. This, I would call that a blue curve, is the graph of negative 1 over x. And this purple or pink curve is the graph of sine of x over x. And notice how your sine of x over x has been perfectly sandwiched in between these other two graphs. Okay, so that'll mean something in just a little bit. But right now, let me show you how you could, just intuitively, how you could arrive at this. Ready? So do you agree with me that sine of x is always between negative 1 and positive 1? Will you agree with me there? The biggest sine of x ever reaches is 1, and the smallest it ever reaches is negative 1. Okay, well, if you will grant me that, what if I just divide everything by x? Okay. Well, in this case, you can just simply, you can see how it is that the sine of x over x is nestled or sandwiched between these other two curves. You can see where the graphs have come from now. So let me put a pin, all right, in this, and we will come back to a theorem that this kind of leads to in a little bit. But for now, I think this is enough for the first video for 1.3. When we come back, we will finish 1.3. See you then.